Okay, so today we're going to get into our last section of chapter 6, which is 6.5. As you can see, molecular geometry. This goes back to what we did in section 6.2 with those Lewis structures that you have to draw. That's going to be one of the first things that we do when we're trying to determine the shape of these small molecules, is determine what their Lewis structure is, and from there, try to look at it in terms of what is the shape of that molecule. Okay? So, just a few things about molecular geometry. We're trying to look for these 3D arrangements of the molecules, atoms, and space, not just flat two-dimensional like we would draw on paper, but try to look at what it would look like in 3 dimensions. Um, Another thing you can determine through molecular geometry is the polarity of the molecule, meaning does it have a negative side? Does it have a positive side? Is there an uneven distribution of electrical charge because of the electrons? We're not going to get into that very much at all in this chapter, but we will talk a little bit about intermolecular forces. So just know that molecules can be polar or nonpolar. That's one of the important things. And that's kind of what we're looking at here. Bonds can be polar, just individual bonds between atoms. If they're identical atoms, remember that bond is going to be nonpolar, nonpolar covalent. And it's equal sharing between the two atoms because they're the same in terms of electronegativity. They have the same electronegativity values. With different atoms, unless their electronegativity is very close, they're polar. Okay, the higher electronegative atom will hold the electrons more of the time, therefore making that partially negative and making the other side partially positive. Okay, and this just is a couple of examples. Here's chlorine bonded to chlorine right down here. This would be a nonpolar bond. You can see the electron cloud here is very evenly distributed around the two chlorine atoms. Their difference in electronegativity would be 0. Here is an HCl bond for hydrochloric acid or hydrogen chloride. Chlorine's electronegativity is 3.0, hydrogen's is 2.1. Therefore, the chlorine holds more of the electrons around it more of the time, therefore making it, remember that little symbol means partial, partially negative, where the hydrogen end is partially positive. Therefore, this molecule is polar. The bond is polar, and the molecule, because it only contains one bond, is polar as well. Okay, so with the polarity of a molecule, if all the bonds are nonpolar, the molecule has to be nonpolar because you have no uneven distribution of electrical charge. Now, and this is just showing you like an H2 or Cl2, something like that in terms of what that molecule would be. Now, when you have polar bonds, you can have nonpolar molecules or polar molecules. Just because having polar bonds doesn't make the molecule polar all of the time. Here's an example here. This is carbon dioxide. It forms a linear molecule, and you're going to see how that is here in a minute. It has two polar bonds, okay? But because the electrons are getting pulled in this direction and in this direction, the molecule itself is actually nonpolar. Now, here's a water molecule. It's a different shape than carbon dioxide. It's what we call the bent shape. And it is a polar molecule, and it contains polar bonds. This H to O bond is polar. This H to O bond is polar. Therefore, the whole molecule is polar. This is a partially negative side of water, and this is a partially positive side of water. So with polar bonds, you can have polar or non-polar molecules. Okay, so how are we going to determine what shape a molecule is? Well, there's a couple ways to do that. The way that we're going to look at is what's called VSEPR theory. And VSEPR stands for valence, shell, electron, pair, repulsion. So remember, the valence shell, those are your outer shell electrons. If they're in pairs, they repel each other and they make the molecule form into different shapes. Okay, and here's the definition of that. If you'd like to write it down in your note guide or just on a sheet of paper, states that the repulsion between the sets of valence level electrons surrounding an atom causes these sets to be oriented as far apart as possible. Okay, so for there's many different shapes that these molecules can take. We're just going to look at the shapes that don't violate the octet rule. Okay, so you're going to draw a Lewis structure. From there, you're going to determine the shape. Okay, so what I included in your Schoology folder was, it says VSEPR and molecular shapes. It's a reference guide that you will use to tell you what shape different molecules are. There's two things that you have to look at in the Lewis structure to determine shape, and that is how many atoms are bonded to the central atom and how many lone pairs of electrons there are on the central atom, just on the central atom. So both things deal with the central atom. So the first thing is anytime two atoms are bonded to each other in just a diatomic molecule, the shape's always going to be linear. The bond angle is always going to be 180 degrees. Those really don't even have a central atom because there's just one thing bonded to another. Now, when you do have a central atom like you see here, and you have two atoms bonded to that central atom, so 1 and 2, and on that central atom, you have no lone pairs. Okay, there's no lone pairs of electrons. It's going to be a linear molecule, and the bond angle will be 180 degrees. So it's just a straight line. It's 180 degrees right there. Okay. Now, if you have three atoms bonded to the central atom, so here's your central atom right here, and you have an atom bonded here, here, and here. It's what we call trigonal planar. Okay. So you have three atoms bonded, no lone pairs, and the bond angles are 120. So what this is, if you look at the name trigonal planar, it's like a flat triangle. I know this one's upside down, but it's like a flat triangle. These angles here, 120, 120, and 120. So it's flat, it's planar, and it looks like a triangle. Okay. Next is your tetrahedral shape. Tetra meaning 4. Okay. And that's when you have 4 atoms bonded to the central atom and no lone pairs on this central atom. It's called tetrahedral in shape. Okay. This is symmetrical. Okay, you can rotate it any way you would like, but it is in 3 dimensions. You can kind of see this one's going back, this one's going back, this one's kind of coming out, and this one's going straight up. These bond angles here are all 109.5, every single one, okay, or 109.5. This is the tetrahedral shape, okay. Now, here's a couple where we have lone pairs of electrons. So if we have 3 atoms bonded to the central atom, and this represents a lone pair of electrons, okay, that you would draw on your Lewis structure, the shape is trigonal pyramidal, okay. What this valence shell electron pair does, it shortens the angle down here from 109.5 to 107. You can see it still looks sort of tetrahedral in shape. It's in the tetrahedral family, but instead of having a bond with an atom up here, it has a lone pair. So the angle is 107. Now, the bent molecule, like water, it has 2 atoms bonded to the central atom. Here's this O and this H, and it has 2 unshared pairs of electrons on the central atom. So it's still sort of tetrahedral in shape, in family, but it's called the bent shape. Its angles are 104.5. I think your textbook uses 105. It rounds it up, but it is, for water, it's around 104.5. Okay. There's one other one on that sheet, and it's where you have 2 atoms bonded to the central atom in 1 lone pair. So it's similar to the trigonal planar, but that 1 lone pair causes those to be angled down further, so it's not 120, it's less than 120. That's called bent also, and we're going to do an example like that. Okay, so what you're going to need is, in your note packet, there's that shapes of small molecules page that's blank, and you're going to need that shape sheet that says VSEPR and molecular shapes. You don't necessarily have to print those out if you just have a scratch piece of paper, and you can pull that sheet up onto your computer. You'll be in good shape. So we're going to do that with part 2 of this lecture. We're going to go through those examples.